Hello, everybody. Here I'm going to solve an eigenvalues and eigenvectors question. So we have a matrix in 3x3 matrix, 3x3 matrix, a real matrix. We would like to find out eigenvalues and eigenvectors. For eigenvalues by definition, is the characteristic polynomial. Characteristic polynomial of a matrix is given by, defined by, determinant of B, and lambda is indeterminate in this case. I is the identity matrix. B minus lambda I is equal to. So this is the characteristic polynomial. We will calculate that, and we will find a polynomial in lambda, and finding the roots of this polynomial will give us the eigenvalues, as we know that from the theory. So I will have another video on the summary of how we calculate eigenvalues, eigenvectors in a theoretical way. But this is an example how we calculate. So the determinant of this matrix, and I is the identity matrix, is, as we know, identity matrices are given by 1 0 0 0 1 0 0 0 1, right? These are the identity matrices. So this just means that this matrix is just, we are taking away lambdas in the main diagonal and calculate the determinant. Okay. So let's use the determinant definition and open it up, this determinant with respect to the first row. So 6 minus lambda, 6 minus lambda, and this is the first row, first column, that is -1 to square, that is positive, and whatever it's left, 1 minus lambda, 2 minus lambda. And then we have the second one here, but this is first row, second entry. So this is this position. It reads the position. So 2 times, that will be minus, and we are going to remove from the first one and second one. I have another video shows how to calculate the determinant and how to calculate the quick way. Okay, if you are adopting there, please go and watch that one as well. But this is how we calculate 3x3 matrices determinants. Okay, then this one will be moved. We have the we need to calculate the determinant of 2 minus 1 to 2 minus lambda. I'm using the straight lines here. Straight lines means the determinant. That's a general notation, and the notation that I'm being using here. For this entry, we have -1, and the position is the first row of third column. So 1 plus 3. -1 to the power of 1 plus 3. So that will be plus, but this one will make it negative. We are removing the first row, last column, and the minor matrix left in here is 2 minus 1 minus lambda, and -1 and 2. So we were going to calculate this little 2x2 matrices, and then calculate this quantity and make it equal to 0, find out the lambdas, whatever the lambda is, that will give us the eigenvalues. Okay, so 6 minus lambda, that one, this is positive, and determinant here, this times this, -1 minus lambda, 2 minus lambda, minus the opposite diagonal, which is -4. Here we have -2, right? This is minus, this is 2, -2. This times this will be 4 minus 2 lambda, that's that one, and minus the opposite diagonal, which is minus, will be plus 2, which is that guy here. Here we have, this one will be +1, this one is minus, so I have a minus here. The multiplications of the main diagonal will give me 4, and multiplications of the opposite diagonal will give me minus times minus, but since it is an opposite diagonal, it will be minus again. So this is why I have -1, -1. This one times this one, minus. Okay, as we know, main diagonal plus, opposite diagonal minus. This times this, minus this time that. This times this, minus this time that, right? Okay, now we need to tidy up this. Leave that one and try to tidy up that. We have -2 minus, so plus lambda from this one, this one, this one, this one, -2 lambda, and this one, lambda square, and we have 4 here, right? And here we have 6. 6 times 2 minus 2 will be -12. We have -2 lambda times -2, that will be +4 lambda. Here we have 3 and minus lambda, so this is -3 minus times minus plus lambda. Okay, we are still tidying up this. 6 minus lambda. We have lambda squared. Here we will have minus lambda, -4 -2 -6. What we have here, -15, that's guy, and 4 lambda plus lambda will be 5 lambda. Still, we need to sum it up, tidy up. So we need to multiply this times this. So we will have minus lambda cube, that's that guy. With the lambda square, we have -6 lambda squared. Yep. I think I've done it in the mind a little, and then to tidy up here later. So let's have a look what we have. Minus lambda, -6 lambda square, -6 lambda square, minus +6 lambda, +6 lambda. This times this 36, that one here. And then lambda cube ones. This one, lambda cube. This one, plus lambda square. This one, plus 6 lambda. Okay, so we have this, and this one does not change as it is. Now tidy up this one a little. We have lambda cube, lambda square. We have -6 lambda square here, lambda square here. That will be -5 lambda square. And the lambdas, we have 6 plus 6 plus 5, right? That will be 17 lambda. And then we have 36 minus 15, that will be 21. So we have this polynomial, and this polynomial is equal to 0. Let's, for simplicity, make it multiply by -1, because the highest term is minus. We don't want to, I would like to work on the positive one coefficient of the highest term in the polynomial. So this is why I'm multiplying with -1. It's equal to 0 anyway, it will not matter. Okay, so this is a cubic polynomial. For a cubic polynomial, we don't have a formula, a general formula to solve it. In order to be able to solve, we usually try a some simple roots to satisfy the equation. For example, 1 -1 -2 +1, they are the ones that we try. And then we divide and try to get a quadratic polynomial. We want something like this. We want a linear factor times a quadratic factor. Then we know how to solve the quadratic factor. So we would like to reduce the problem to the quadratic polynomial situation so that we can solve. It's up to you how to solve this, whatever the knowledge you have before, but you need to find out the roots of this polynomial in order to be able to find out the eigenvalues of the matrix. That's the duty of it, right? Find the roots of this polynomial. For me, if we put the lambda is equal to -1, my way of doing it, check it out. Let's see whether I've got lambda is equal to -1 as a root. -1, 5, 17, -22. So this is 22 minus 22 is equal to 0. So lambda 1 is equal to -1 is a root. So I want to factorize this polynomial into a linear factor. I found a linear factor. Linear factor, since lambda is equal to -1 is a root, lambda plus 1 is a linear factor. Lambda plus 1 is a linear factor. Then I need to figure out what is the quadratic part of this factorization. So my aim is to write it down in this fashion. Right? In order to be able to find this thing, we divide this polynomial to this linear factor to get whatever is left. So this is a polynomial divided by lambda plus 1. So, well, this is the way that I do my division calculation, but some people does in a different way. They put the main polynomial here to divide, and this is the divisor. So that's a polynomial, this one divided by this. They write the answer here and then do the calculations here. It doesn't matter whatever you get used to it. It is just a division. You need to do the division by your hands in order to be able to figure out the factorization, or whatever the method you're used to. So we have a lambda cube here. So then I need to multiply with the lambda square, lambda cube plus lambda square, and subtracting it, I will have 5 lambda square here, lambda minus lambda square. I will have 4 lambda square. Then the rest stays. So for 4 lambda square, I need to multiply with the 4 lambda, multiplying 4 lambda square minus 4 lambda. This one and this one will give me minus 21 lambda and minus 21. Then if I multiply this minus 21, then I will have 0. If I don't have a 0, there's something wrong, because we should be able to write it down, these equations, as a linear product and a quadratic polynomial product. Because lambda is -1 is a root. It means that it is divisible by lambda plus 1. As the theory tells you. Once you find out that this is a root, it means that this is a linear factor. Then whatever is left, it has to be a quadratic polynomial, because the order of this polynomial is 1, and order of this polynomial is 2. 1 plus 2 is 3, and that is 3. So this is the theory tells you it has to be. So you have to have a 0 here. If you couldn't find a 0, it means you've done something wrong. Okay, now we are on the right track, because we have a quadratic polynomial. We write it down, a cubic polynomial, in terms of a linear factor and a quadratic factor. Now quadratic factor is easier for us to figure it out. You can use your quadratic polynomial solution formula, or try to do it with the linear factorization. This can be found as a linear factorization. That's lambda square. 7 lambda minus 3 will give us the 4 lambda, and 3 times 7 is minus 21. That will work. So this is correct. So these are linear factorizations of this cubic polynomial. This gives us immediately the solutions of this polynomial, which are the roots of this polynomial. So lambda is equal to -1, and from this factorization, this linear factor, we have 3. From this linear factor, we have -7. -1, 3, and -7 are eigenvalues. So we found eigenvalues. Now the next task is to calculate the eigenspaces for each eigenvalue. Let's start from lambda 1 is equal to -1. So lambda 1 eigenspace, there are several ways to write it down for the notation. And this is the notation I'm using it. This is the eigenvector space with respect to the lambda 1. So E minus 1. By the definition, eigenspace means that kernel of B minus lambda I. Lambda I in this case is -1. So minus will be +1. So we need to calculate this kernel, which means that you have the B matrix and you will add 1 on the diagonal, right? You have the B matrix here, which is the B matrix, you will add ones. So you will have 5 minus 5, 0, and 3. Okay. And the others will be the same. Minus 5, 0, and 3. Others are the same. We need to calculate this kernel. This is a subspace, which is an infinitely many vectors in it. Right? By the definition of the kernel space, that is the we are searching. Our aim is to find out a solution of this equation. This is by the theory, and this by the definition of the kernel. I are looking at what are the three vectors in three-dimensional space satisfying this condition. Yeah, clearly this needs to be plus. See here. We are not changing the equation. So we wanted to solve this homogeneous equation. Homogeneous in our system of equations. Homogeneous means the right-hand side is 0. Okay. Now it means how we can solve this system. We usually write it down augmentation matrix, but the augmentation matrix involves with the zeros. I don't have a 0, 0, 0 here all the time to write it down. It is not necessary. Or all I am taking this equation, this matrix, and applying the row operations to get the reduced row echelon form to find the vector V and understand this vector space kernel, which is an eigenspace corresponding eigenvalue lambda 1 is equal to minus 1. Here we want, I think I wrote what I've done here. I interchange with the second row multiplied by 1 over 2, because this will be 1, 1, and putting into the first row, and then the first row to the second floor, because I want this position is 1, and I want to get these two positions 0. Right? So in order to be able to get these two positions 0, I multiply the first row with the 5, and add here, multiply, this is 1, so just add the first row to the third row. So the first row will not change, that will be 1, 0, 1. And the second row will be the 5 times the first row. So that will be 0. This position will be 0. This is 0, will affect nothing. So that is 2. And then we will have 1 here. We multiply by 5. That is 5. 5 minus 1 will be just plus 4. For this last row, this will be 0. This entry will be 0. This was what we aimed for. And then this will not affect at all. That is 2. And this will be just an addition. We add this and this entry, which will be 4. Okay, we can make this one, divide by this one, 2. And then add, multiply by minus and add this one. We will get 0, 0. That is really clear. We don't need to write it down. So this is the matrix. Now we can write everything in terms of these. We can multiply. I change it as a V or the X. X's are V's are here. So what we are doing here, we are looking at like V1 or X1. We are looking at the solution of it. X1, X2, X3 is equal to 0, 0, 0. We don't need to write it down this, but this is what we do, right? This is the in our mind. In our mind, we are multiplying this row, multiplying this row with this column, we are making it equal. Multiply this row with this column, make it equal. Multiply this one and this one, make it equal. So this is the definition of that one, right? This is the extended form. We know this, how to calculate this kind of things from the first year. Okay, for the first row, we have x1 plus x3 is equal to 0. From the second row, we have x2 plus 2x3 is equal to 0. The last row could be anything. That is 0 times x3 is equal to 0. It means that x3 is a free variable, is a parameter for us. So when we say x3 is equal to something, let's say mu, the mu is any real number, then we can decide x1 and x2 in terms of the mu. So x1 is minus mu because x1 is equal to minus x3. x2 is equal to minus 2x3, where that is x2 is minus 2 mu. That means x here, minus 1, minus 2, 1 mu, right? From here, in a vector form, we obtain this vector. These are all the solutions of this space. So it means that these kind of vectors makes this space, right? It means that the kernel space of B plus 1, which is the ion space, minus 1 ion space, is the span with this vector, minus 1, minus 2, 1. And the spanning, this is what it means. Spanning means some constant, infinitely many constant times a particular vector is the span of that vector. Okay, now we usually, as a matter of fact, every vector in this infinitely space, this is a vector space, so it has infinitely many vectors in it. Every vector in that vector space is an ion vector corresponding to eigenvalue minus 1. But we can always choose an infinitely many vectors of it because we are multiplying mu. You can change it anything that you like. So there are infinitely many choices as well. The choice that you made, you said this is the basis for this ion space, which is what we've done here. So this vector minus 1, minus 2, 1, we choose as a basis. I mean, we calculate it, and we know that as a basis of the E minus 1. But we particularly take this one. We didn't sort of multiply in other mu's. Okay? So that vector is particularly, we say, minus 1 ion vector. This is a bit confusion because actually the ion vectors, minus 1 ion vectors are infinitely many. When we are talking about minus 1 ion vector, we mean is the basis of the minus 1 ion space that we choose. I think that's what I'm trying to say here. So the infinitely many minus 1 ion vectors as mu runs through, but we say minus 1 ion vector is minus 1, minus 2, 1, that particular one that we are talking about in that question. Okay, this was the first ion space. Now we have another eigenvalue, lambda 2 is equal to 3. Let's calculate lambda 2 is equal to 3 ion space. Okay, that is, again, lambda I. Lambda I is 3. So minus lambda I, minus 3. So we are 3, lambda 2 is equal to 3 ion space, E3, which is the kernel of B minus 3I. Only we will subtract 3 on the main diagonal. So that will be minus 9, minus 4, minus 1. If you look at that in the main question. So this is minus 6, minus 1, minus 2. So your eigenvalue is 3. So you're subtracting the 3 on the main diagonal. Minus 3, minus 6, minus 9, minus 1, minus 3, minus 4. 2 minus 3 is minus 1. So this is the diagonal, main diagonal, and nothing changed on the others. Same idea, we would like to solve this linear system of equation, homogeneous linear system of equation. I haven't wrote, but this is the case that we want to find out. This is this. So this is the kernel space. We would like to find out the solution space such that B minus 3I x is equal to 0. We want to solve this space, homogeneous equations, homogeneous linear equations. Okay, what we've done, So this is row 1 and row 3. I can interchange this one and this one multiply by -1. I think that's what I've done here. So I have 1, -2, 1. That will be the first row. And the first row will be the third row. Just I swap this one and multiply this one by -1. So this matrix, this one or 2, so I want this position is 0 and this position is 0. We multiply the first row, add to the second row, that will give this position is 0. And if we multiply first row by 9, add to the third row, we get this position 0. Okay, then the first row, nothing will change, 1, -2, 1. And the second row, the summation will be 0. Everything will turn to 0. And the last row, we will have 9, that will be 0. 9, 18, 18 plus -18 plus 2, -16. And then multiply by 9 -1 will be just 8. So we can swap this row and divide this one by 8 and multiply by -1. We obtain this. We can go one more step. We can make this position is 0, which will make a little easier when we are turning back to our equation x1, x2, x3. You can leave it like that. You can figure it out, multiply by x1, x2, x3, and work it that way. But you will need to do a few row of algebraic way to get this place. So you can leave it like that, but I prefer to get this position 0. Okay, that's my aim. So I will do it in matrix form rather than an algebraically by hand. Okay, so I have this one. If I multiply this second row, I just add the second row with the first one, then I will get 0, 0 in this position. I will have 2 -1. I can make this one too, but I don't need to because I want to calculate x1, x2, x3. X1 is equal to 0, definitely, from here. Again, you are thinking, you're multiplying this with the vector x1, x2, x3, and make it equal to 0 vector. So the x1 is equal to 0, 2x1 minus x3 is equal to 0, and then 0 x3 is equal to 0. So x3 is free. X3 can be anything. So let's say x3 is equal to mu as any real number. So that's a parameter. And these equations needs to be written in terms of a parameter. Here, this one implies x2 is equal to 1 over 2 x3. Then, well, x3 is equal to mu. Substitute mu here. Then we will have x3. Well, in order to be able to not to have the quotient, we can have x3 is equal to 2 mu, x2 is equal to mu. So we will have a vector with integer elements. So this is why I have 2 mu. Since mu is infinitely many, can be anything in the real numbers, to choose 2 mu will not create any problem. So this is the vector. So the solution space for the 3 ion space, this space, is all of these vectors when mu is running through the -infinity to +infinity. So this is the solution space. And this vector here is the basis of that solution space. That is, so the E3, the 3 ion space, the kernel of B minus 3i is the span of this vector. And the 3 ion vector we call 0, 1, 2. So this is the second ion vector. Now we would like to find out the lambda 3 is equal to -7 ion space. So E minus 7 is the kernel of the B minus 7i. So that will be the plus 7. We are going to add 7 on the main diagonal of the matrix B. If you do that, we obtain this matrix. Yep. Let's show the main diagonals of B, which is this guy. We are adding plus 7, 7, 7, 7. So this one is plus 1. This one is plus 6. And this one will be 9. This is 1, 6, 9. Okay, we would like to solve, this is the kernel space. We would like to find the solutions of this matrix times, so the vectors is equal to 0 vector. That's what we want to do. So R1 is correct. This position is 1. That's what we like to do. We can make this position 0 immediately by just adding these two rows. Yeah. And this one plus this one will be 4. This one plus this one will be 8. Now the second row, we divide the second row by 2. Yeah, because everything is multiple even. They can divide by 2. That's 1, 3, 1. And multiply the first row by minus 1 and add to the second row. That will make this position 0. That's what we like. That's what we are aiming for. This position is 0. This 3 minus 2 will be 1. Minus of this one will be plus 1. And adding this one will be 2. So that's the second row. We can make this, where we have too much, 4 is a common factor. We can divide by 4. Then we will have 1, 2. So since we have two same rows, one of them will be 0, 0, 0. So let's make the last row 0 as we get used to it. This position, we can make it 0 because if we multiply this by minus 2, add this up, this position will be 0. It will simplify our calculation. Yeah. So that is 0. We multiply this by minus 2. So that is minus 4. Minus 1 will be minus 5. From this last row, we find that x3 is a free variable. Some mu is a real number. From the first row, x1 minus 5, x3 is equal to 0. From the second row, we have x2 plus 2x3 is equal to 0. So this equation implies that x1 is equal to 5 mu, because x3 is mu. x2 is minus 2 mu, and x3 is mu. So the vector here we have 5, minus 2, 1. So the is minus 7 eigenspace, which is the kernel of B plus 7i, is the spanning space of 5, minus 2, 1. And we call minus 7 eigenvector is 5, minus 2, 1. I think that's enough for this video, and we will solve more eigenvalues and eigenvector problems in the subsequent videos. Thank you very much. Cheers.